So far we have been talking about what parameters we can use to classify the orbitals. We have not exactly included the electrons in all this conversation. So the question is how many electrons can you fit in one orbital? And this may be a trivial question if you think of from what you learned in the past, but it's not so trivial because we have used quantum numbers to classify orbitals, but we do not know how many electrons you can place in each orbital. We have two options. Option one would be that all of our electrons are all in the same orbital. You could say that they get along very well, okay? The option two would be that each and every one of the electrons are in separate spin orbitals, not only orbitals but spin orbitals. In other words, if in the 2s one electron is pointing up, the other one is pointing down. That is, each and every one of the electrons have a different set of quantum numbers. Well, it turns out that for the characteristics of electrons, the electrons need to be in a different set of quantum numbers. The electrons need to be in an orbital completely different from any other electron. This is the so-called Pauli's exclusion principle, named after Wolfgang Pauli. The more physical explanation for that is that all fermions, what's a fermion? Fermion is a particle with a fractional spin. Does an electron have a fractional spin? Yes, we said that the ms can be 1 or minus 1/2. So as opposed to a boson, and you may not know what I'm talking about, but a boson is a particle with an integer spin. A photon, for example, is a boson. That a boson would behave in this way. Fermions, like electrons, all particles with fractional spin, will obey the so-called Pauli's exclusion principle. So Wolfgang Pauli is this gentleman that you see in this picture, was the first one to come up with this principle, and a metaphor that sometimes works to understand what we mean by that is that the same way that when you go to, say, a baseball stadium and you buy a ticket, your ticket will contain a section, a box, a row, and a seat. And you hope to find that seat empty, right, so that you can sit on it. So electrons behave a little bit like that. They need to have a specific set of quantum numbers, section, box, row, seat, or N, L, M sub L, and Ms, that no other electron has. That's a little bit how they work. So if you think of a 2s, and you can only fit 2 electrons in a 2s because there's only two possible combinations of quantum numbers that fit in the 2s. Let's run an example. Maybe this will make a little bit more sense. So in this case, for example, is showing you the fluorine atom, and the electronic configuration of the fluorine atom is represented with this diagram. We will explain in a second what this diagram says, but it's asking to find the quantum numbers for the 3rd and for the 8th electron. It does not matter in what way we count the electrons, this is not important, but let's say that we want to know what is the set of quantum numbers of this electron. Why this one? Well, it's the 3rd, 1, 2, 3, alright, and the 8th, we can start just counting from the left, 1, 2, 3, 4, 5, 6, 7, 8, alright. Do these two electrons have a completely different set of quantum numbers? So do they obey Pauli's exclusion principle? Let's see. For this one, what is principal quantum number? The principal quantum number is 2 because it's in a 2s orbital. What is the angular quantum number? The quantum number is 0 because it's in an s orbital. What is the M sub L? Well, S, when the orbital is S, the M sub L can only be 0. Okay, and how much is Ms? Let's say just we need to come up with a standard, so let's say if the arrow is pointing up, we're gonna say that this is positive 1/2. It does not matter if it's up or down, but as long as we are consistent with the other electrons. So let's see for this electron here. What is the principal quantum number? It's 2 the angular momentum quantum number is 1 because it's a p. Now, if the way they're displayed here, again, this is all very relative depending on how you define it. We're gonna say that we start with the m sub l negative 1, this is the 0, and this is the plus 1. So if it's in the box in the middle, the m sub l is gonna be 0. Okay, and if we said that pointing upwards is an ms of plus 1/2, now it's pointing downwards, it has to be minus 1/2. So you could do the same for the other electrons, and you will see that all of the electrons, because they obey the exclusion principle, the Pauli's exclusion principle, all of the electrons will have a different set of quantum numbers.